In this video, we are going to be going over chemical quantities, but specifically in reactions. So in the beginning of this chapter, we learned how to do different manipulations in which we converted from moles to atoms, from atoms back to moles, from moles to grams, and grams back to moles. We even learned the relationship between elements within a compound and the moles of a particular compound. And now all of those different calculations we're going to be applying to chemical reactions. So when it comes to this, as you can see, here we have a chemical reaction in which iron combines with sulfur, and we are going to be generating iron 3 sulfide. Now, understand that whenever we have a chemical reaction, as we already established earlier in the chapter, we need to first write the balanced chemical equation. The reason why this is important is that with the balanced chemical equation, then you can understand what is the relationship between reactants and products. So for example, if we have the following reaction, and now that it has balance and it has the proper coefficients in it, we can read it as 2 moles of iron react with 3 moles of sulfur to produce 1 mole of iron 3 sulfide. What does that mean? That if we want, we can make mole to mole relationships between any components of the reaction. So as you can see, the first is going to be the relationship between reactants. Meaning that thanks to those coefficients, we can say that for every 2 moles of iron, that is going to react with 3 moles of sulfur, and vice versa. Because remember that this relationship, since it can be placed as a fraction, we can just put the relationship in the numerator or the denominator. We can even make relationships of a reactant and the product. And that's what we see in the next two, in which we can say that for every 2 moles of iron, we're going to be producing 1 mole of iron 3 sulfide and vice versa. And lastly, we can relate it to the other reactant. So we can say that every 3 moles of sulfur, we'll be producing 1 mole of iron 3 sulfide. Now, we can utilize this to actually make calculations, because one of the things is that whenever you're doing reactions in the laboratory, we want to know if you have enough of both reactants, how much product are we ideally going to be making in the reaction? And as you can imagine, in industry, whenever things are being made, it doesn't matter if it's plastic or it is a food type or it is a drug, a medicine. It is important to know how much we're going to make depending on how much we start with. So as you can see, in this problem, the question states, how many moles of iron 3 oxide can form from 6.0 moles of O2? So whenever you're looking at relationships in chemical quantities based on a chemical reaction, understand that you need to have a balanced chemical equation. Now, I am going to be introducing the flow chart that you're going to be utilizing when we are going to be doing these problems. So when it comes to chemical quantities and reactions, this is the flow chart that we're going to be utilizing. We're just going to make it larger and place it right here in the slide. So when it comes to this, understand that if you're asking for, so if you're given moles of any component of the reaction and you need to find the moles of another component, this is the flowchart that you're going to be utilizing. Here, A and B are just relative. That just means one substance next to the other. So it is not particularly assigned. In other words, A is always going to be what is given. B is what you need to find if you want to define a terminology. So in this case, because you start at moles, understand that moles of a substance was given, you need to find the moles of the other substance. So in order to do that conversion, so these are the conversion factors, you need to utilize the mole to mole factor. Okay, and the mole to mole factor is basically based, I'm just going to put it right here in the corner, mole to mole factor is based on the coefficients of the balanced chemical equation. So when we're trying to accomplish this conversion, we're only focusing on this particular portion of the flow chart. Okay, so let's write the setup. So for here we have 6.0 moles of O2, and we only have one conversion factor, which is the mole to mole ratio. I look at my chemical reaction. I see that the relationship is, let me highlight it. 3 moles of oxygen relate to 2 moles of iron 3 oxide. So that's what I'm going to utilize in my mole to mole factor. In the bottom, because I need to cancel the moles of O2, I'm going to put 3 moles of O2. And in the top, I'm going to put 2 moles as Fe2O3. And then when I do this, I'm going to multiply 6.0 times 2 divided by 3. And even though the value that the calculator gives me is 4, I need to report the correct number of suffix. So I'm going to say 4.0 moles of Fe2O3. And this is how you do a problem in which you are given moles of one substance and you change into moles of another substance within a chemical reaction. Now, we also have mass calculations in reactions, okay? And when it comes to mass calculation, understand that pretty much what we're doing is changing from grams of one substance to grams of another. So one of the things that this is illustrating is just giving you an example of a reaction. This is acetylene, and acetylene has the chemical formula of C2H2, and it's been reacting with oxygen to make a combustion, okay? So when this combustion occurs, again, you make CO2, water, and energy. So we can actually calculate what is the mass of acetylene that is used to weld a specific mass of metal. So understand that whenever we are doing mass-to-mass calculations, we're going to be utilizing the same flowchart that I just introduced to you, that we utilize to compare moles of 2 substances within a chemical reaction. Remember that in the previous problem, we were giving moles of one substance and we were trying to determine more moles of another. Now, remember, given a balanced chemical equation, we can convert the mass of one substance to another substance by first converting the mass of the substance to the moles. Then we can do the mole to mole relationship between them, and then lastly utilizing the molar mass of that second substance to find the grams. So let's do an example in a mass to mass conversion. So as you can see here, it says Suppose that we want to determine the mass in grams of ammonia that can be produced from 32 grams of N2 in the phylochemical reaction. So for this problem, again, we are converting from one substance to the other. So we're doing the whole sequence, okay? We are given grams of one substance, that in this case is 32 grams of N2. And what we need to find is grams of NH3, okay? That is what is happening overall. So this is how we set up the problem. Understand that we're going to need 1, 2, 3 conversion factors. So I'm first going to write the amount that is given to me. 32 grams of N2. And I know I have the 3 conversion factors. I'm going to try to put the conversion factors under each of the boxes so you see where we got them from. So as you can see, the first conversion will be converting those grams given of a particular substance to the moles of the substance. So as here, because we're working with specifically N2, all we're doing is taking the mass of nitrogen and multiplying it times 2, which is something that we learned before. The mass of nitrogen is 14.0067. We're going to multiply it times 2. So that gives us a mass of 28.0134 grams of N2 in 1 mole of N2. So molar mass is something that we learned how to calculate before. Then we're going to use the mole-to-mole factor. Remember that the mole-to-mole factor comes from the coefficients in our balanced chemical equation. Also remember that we want to cancel diagonally. So here, by looking at it, the coefficients of this is 1, 3, and 2. So the relationship here is that for every mole of N2, that corresponds to 2 moles of ammonia, which is the other substance that we're interested in. Then lastly, as you can see, we're going to be utilizing the molar mass of that second substance. And we know that when it comes to molar mass, we're going to say 1 mole of that second substance, which in this case is going to be NH3. And we need to find the grams of NH3. So in order to do that, we're going to multiply 1.00794 times 3. Those are the 3 hydrogens. And we're going to add that value to the mass of nitrogen, which is 14.0067. So the molar mass for ammonia is going to be 17.03052. Now, all of that, now, as you can see, we're going to multiply the top, which is going to be 32 times 2 times 17.03052. And then we're going to divide that value by 28.0134. And as you can see, that is multiplied by 1. So we're just going to divide by that number. Okay, so as a value, we get 38.90 in a series of numbers, but because 2 sig figs were given to us, then we need to round this to 2 sig figs. So the final value is going to be 39 grams of NH3 is what is being created in this process. Now, in the in-class worksheet, as you can see, we have a whole page that we can practice the relationships between chemical quantities. And as you can see here, there's several parts to it. So this is where we're going to tie it in everything we have done so far. As you can see here, the first thing that we're doing is writing the balanced chemical equation. Okay, and the equation given is calcium chloride. So I'm just going to zoom in so we can look at it closely. So the first item is going to be writing the balanced chemical equation. When it comes to the balanced chemical equation, I hope that you can identify that this is a decomposition reaction. In which what is decomposing is going to be calcium chlorate, which the chemical formula is CaClO3 2. And that is going to be decomposing to calcium chloride, which is CaCl2, and is going to be decomposing to oxygen. Now, this is oxygen gas, okay? Or molecular oxygen, which means that this is going to decompose to O2, okay? So to balance this chemical equation, we need to place a 1 on the calcium chloride, a 1 on the calcium chloride, and a 3 in the molecular oxygen. Now understand that the number ones don't need to be placed. I just decided to place them so you guys will be able to see it. Now, let's go through the different questions that we have here on this part of the worksheet. As you can see, the question 1, it says, how many moles of oxygen, okay, and remember that we're talking about oxygen gas, will be formed if 2.84 moles of calcium chlorate decompose, okay? So here we're looking at a molar to molar relationship. So we are given moles of one and we need to find moles of another. So we're doing this, and remember that that mole to mole factor is going to be our conversion factor. So to set up this problem, what we're going to do is write the amount given, 2.84 moles of calcium chloride and then we're going to look at the mole to mole factor based on our chemical equation. So we're going to say 1 mole of CaClO3, then there's 2 of them, correspond to specifically 3 moles of O2. So when we multiply those two values and we report it to 36 figs, this is going to be 8.52 moles of O2. In the next question, it asks, how many grams of calcium chloride will be formed if we start with 1.93 moles of calcium chlorate? So, as you can see here, we are given moles of a substance and we want to find grams of another substance. So as you can see, we are only going to do this portion of the conversion, or I should say of the flow chart. So we have, in this case, 2 conversion factors. We're going to utilize first the mole to mole ratio to find the relationship between moles of A and moles of B. And then lastly, we're going to utilize the molar mass of B to get the grams of B. So this is how we set up the problem. We start with the 1.93 moles of CaClO3 2. We find the molar relationship between the 2 compounds, which is going to be calcium chloride and calcium chloride, and their mole to mole relationship is actually 1 to 1. Then lastly, we're going to utilize the molar mass of calcium chloride to find our final answer. So when we multiply 1.93 times 110.98, then understand that the final answer is going to be 214 grams of calcium chloride. The last question is going to be given specific grams of one substance, can we obtain grams of another substance? So the question reads, how many grams of calcium chloride were used if 3.36 grams of calcium chloride were obtained? So in this case, we're given grams of one substance. We need to find grams of another substance. So remember, we have 1, 2, 3 conversions when we're trying to do that. So let me set out the problem. This is going to be 3.36 grams of calcium chloride. We already know the mass of it, which is 110.98 grams of CaCl2, 1 mole of CaCl2. That is going to be our first conversion factor, the molar mass of A. Then we're going to do the second conversion factor, which is the mole to mole factor. We have 1 mole of CaCl2 related to 1 mole of CaClO3, 2. And remember that comes from the balanced chemical equation. And then lastly, for the last conversion, we are going to find the molar mass of calcium chlorate. So in 1 mole of CaClO3, 2, we're going to have 206.976 grams of CaClO3, 2. So when we do this, I'm just going to write it up here. When we round our final result to 3 6 is going to be 6.27 grams of CaClO3, 2. As you can see, this decomposition can also be utilized as a oxidation reduction reaction. So when we analyze the reaction itself, which I am just going to rewrite the reaction here in the corner. I'm just going to use a different color. So we have ClO3, and there's 2 of them. And then we have calcium chloride plus O2. When it comes to this reaction, the first compound is an ionic compound. So understand that for this ionic compound, we're going to break it into ions. So this is going to have a charge of +2. The ClO3 is going to be overall -1. Understand that a polyatomic ion, it is actually a covalent compound. So I'm just going to move it to the corner to explore how to determine those. So ClO3 -1. Remember that in this case, the second nonmetal is what determines the oxidation number. So oxygen has an oxidation number of -2 that it needs to be multiplied by that 3. So that means that I have an overall value of -6. And because the overall charge of this polyatomic is -1, then that means that chlorine has an oxidation number of +5. Okay? So chlorine is +5. It's a little bit hard to see. Let me just erase it. But you can see the work on the other side. So chlorine is positive side, +5, and then oxygen is -2. When we come and look at The calcium chloride is an ionic compound. So calcium is going to have an oxidation number of +2. Chlorine is going to have an oxidation number of -1. Oxygen, because it's in elemental form, has an oxidation number of 0. Okay? So overall, if we make the list, calcium started at +2, it ended at +2. Chlorine started at +5 and it ended being -1. Oxygen started as -2, ended at 0. So when it comes to oxidation or reduction, okay, because chlorine went from a positive value all the way to a negative value, that means that it got reduced. And went to the oxygen went from a negative value of -2 to 0. So that means it got oxidized.